I begin by thanking the organizers for putting together this very nice conference and for giving me a chance to present some work we have been doing over the last few years. So I'm going to talk about the decay model and variants of the decay model and various phase transitions and a bunch of stuff. I mean, don't be intimidated by the number of slides I'm threatening to hurl at you, but hopefully the density of information per slide is not too high, and I think it is a reasonable target. We will see. We'll do as much as we can. So it is, I'll start by acknowledging the team. So we have Pragnya Das, who's the main sort of workhorse of this, almost everything that I'm going to show. She's a PhD student who's just submitted her thesis. So in fact, what I'm going to describe is almost entirely is like a big chunk of her thesis is going to be thesis work is going to come at you today. And so Devendra Singh Bhakuni is a former PhD student who is currently a postdoc at ICTP. And Pragnya Das is soon going to be a former PhD student, and we'll start working with Lev Vidmar, who's also around. So, and Leah Santos is going to be around next week. Unfortunately, I'll not be able to catch up with her because I'm leaving sooner. And Sebastian Wooster is a colleague at IISER Bhopal, who's also part of one of the projects, which I will try to touch upon if there is time towards that. Okay, so yeah, acknowledgement. So let me, at the outset, flash this acknowledgement, which is part of our paper as well. So ICTS features in a big way in one of the projects that I will discuss. So where Leah Santos was around a few months ago, and Pragnya happened to get a good chunk of time with her. Discussions helped to bring this paper to fruition. So we'll start by acknowledging gratitude to ICTS for putting together so many wonderful events. And yeah, I mean, of course, we're grateful for funding resources and so on, funding agencies. Okay, so the way I've organized my talk is as follows. There are 4 different sections, and each section corresponds to one paper, which was written along with Pragnya and a few others. Each of them is upon PhysRev A, and in fact, one paper just got published yesterday. So we have to talk a little bit about it. We'll see if we'll get to it. That is going to be section 4. Okay, so we'll start with the decay model. So, and so this section is about this, more or less about this paper, where we revisited the phase transitions of the decay model, and we looked at various interesting perspectives which can be obtained if you look at some of the eigenvector properties. So the main message from this part of the talk is going to be that I mean, the decay model itself exhibits a variety of very interesting phase transitions. This is kind of well known. It's been around for several decades. So we were interested in the quantum phase transition, and which is a phase transition from the so-called normal phase to the superradiant phase, and how this is marked by a dramatic change in the scaling of the participation ratio. So the localization properties, are very interesting. So we would highlight how the ground state, as it goes from the superradiant, from the normal phase to the superradiant phase, it exhibits multifractality in the superradiant phase. So this is going to be one highlight which I want to make. Then there is a thermal phase transition, so for which there is an exact analytical expression which is available, which has been written down a long time ago. But we'll show that the same transition temperature can be strikingly captured with the help of mutual information between 2 spins. I will give you all details. This is like the main message at this point. I will go into all the details in a little bit of in a while. So then there is something called the excited state quantum phase transition, right, within the superradiant phase. And so we show that in fact there are 2 cutoff energies. It helps to think of a central band, which is separate from an upper band and a lower band of energies. And the central band shows distinct and interesting properties, which are also captured by eigenvector properties, right, which help corroborate this finding. Okay, so the decay model Hamiltonian is like here. So there is a free part, so it's a bunch of n atoms or n 2-level spins, which all of which have the same level splitting, which is omega naught, and then there is a bosonic field, a single mode bosonic field with frequency omega, and so they're coupled with this coupling G, right? So this is the decay model. So all of these atoms, they don't talk to each other directly, but they are connected to each other via the single mode bosonic field which is present. And so we will work in it corresponds to like a pseudo spin with length J, and you have overall n atoms which is equal to 2J, and so the standard commutation relations and things hold for the bosonic operators and for these angular momentum operators in a standard way. Now, so the basis of the full Hilbert space is like here. So there is this small n which corresponds to the bosonic states, which actually go from all the way from 0 all the way up to infinity. But for our numerics, we will truncate this bosonic mode at some n max, and then we will look at a finite Hamiltonian, right? Because we are doing this truncation, and so the number of atoms is taken to be capital N, and we consider the symmetric subspace in which we fix small j to be just n by 2, and this allows small m to take capital N plus 1 values all the way from minus n by 2 to plus n by 2. Therefore, the dimension of the Hilbert space that we'll be working in would be n plus 1 times n max plus 1, corresponding to the spin part and the bosonic part separately. Right? So in the thermodynamic limit, it is known that there is a second order quantum phase transition from the so-called normal phase to the super radiant phase, and at GC, which is has been shown long ago to be square root of omega naught, the whole thing divided by 2, right? So yeah, we'll work in units where typically omega equal to omega naught equal to 1, unless I say otherwise at some point. Okay, so the quantity of interest for us is the so-called inverse participation ratio, so which helps us characterize the degree of localization, delocalization in an eigenstate. So it's just computed taking all the coefficients which make up your overall eigenstate, and then taking the power 4 and then adding them up. So that is the inverse participation ratio. It's a useful quantity. I mean, so if the state is localized, then you would immediately see that there's only one of these coefficients would be 1. Therefore, IPR would be 1, and also it would be 1 regardless of the system size. On the other hand, if it is completely delocalized, then all of these coefficients would be 1 over square root of ND. And so if you take the 4th power, then it's going to give you 1 over ND squared, and then there are ND of these. So you'll get a 1 over ND, right? So the scaling is important, and we'll come back to this when I show you some data. And a generalized version of this is to consider these, Q dependent IPR, if you wish, and corresponding to that is a Q dependent participation entropy. So from which one can actually extract a multifractal dimension, right? So if you put Q equal to 2 in this expression so in this expression, if you put Q equal to 2, it's going to get you back to this IPR, the standard inverse participation ratio. But essentially, this dq is a measure of how this IPR or generalized IPR would scale with your dimension of your Hilbert space. Okay, so now I have some data which I want to show you, which is about, for the ground state of the decay Hamiltonian, if you look at IPR and then look at how it varies as a function of this coupling strength G, you'll see that beyond G equal to 0.5, you enter a different phase, so which is well known. So, but what is interesting is that the IPR it falls dramatically beyond this point, and it's helpful actually to look at the participation ratio, which is shown in the inset here, and you see that once you enter the superradiant phase, and so deep in the superradiant phase, in fact, so there's a clear dependence on n which emerges, and how this PR varies with n, and therefore the Hilbert space dimension is also interesting, and that is shown in the inset here, right? I mean, so you can see that this PR in the participation ratio in the superradiant phase, deep in the superradiant phase, this is at some point G equal to 4, it goes as square root of ND, right? So this is consistent with dq. So I've shown you data for dq for different values of q, I think 1, 2, and some larger value. But yeah, so it is, so this value is somewhere around 0.5. So it is consistent with a scaling of square root of ND. So which is a signal that this ground state is actually multifractal in the superradiant phase. So this is one message which I want to convey. And the other is, I mean, so there is this whole calculation for how to compute the transition temperature, which I will skip. So there is a way to write down the partition function, and one can write it in terms of these integrals and do a method of steepest descent and extract the transition temperature, right? So this is well known. So what is interesting is that if you start in the superradiant phase and increase the temperature, there is a critical temperature above which your system will again go back to the normal phase. And so this is also nicely captured with the help of mutual information. So mutual information, so we have these, you have a bunch of n spins which are all coupled only to the bosonic field. And so each spin is indirectly coupled to every other spin. So if you look at the quantum correlations that develop between any two spins, so it turns out that in the superradiant phase you have very high values for the mutual information. So mutual information is a useful quantity when your density matrix that you're working with is mixed. So which is indeed the case, because you're also turning on temperature and your overall state itself is in a mixed state, and then you're tracing out the degrees of freedom of everything other than two spins, and then you're asking for the mutual information between spin 1 and spin 2. It doesn't matter which two you consider, because all pairs are essentially the same. So then you will see that in this region, in the superradiant phase, you get a much higher value for the mutual information, and it's a nice marker for this transition, right? So this is one of the messages we want to convey. And then when it comes to the ESQPT, so that is this excited state quantum phase transition. So I said that it's useful to think of these as like made up of 3 different bands. So first of all, if you're in the normal phase, so this is G equal to 0.2 is a tiny value and you're in the normal phase. So the level statistic distribution is well captured by a Poisson distribution. But now if you're in the superradiant phase, if the central band is consistent with a Wigner-Dyson distribution. On the other hand, if you look at energy levels drawn from an upper band or from a lower band, so you have kind of a mixed behavior, but with a closer tendency towards Poisson rather than Wigner-Dyson. And so this is also seen in terms of the ratio of consecutive level spacings. If you study this, you see that when you're in the normal phase, it's consistent with a Poisson value, whereas the central band goes to the Wigner-Dyson value, whereas the top band and the bottom band are they show deviant behavior. And so this is also seen in terms of some eigenvector properties. I don't want to go into all the details, but essentially, so there is these 2 different kinds of entanglement one can study. So one is just the familiar von Neumann entanglement entropy between, you can look at the entanglement between all the spins together with respect to the bosonic field. And so another interesting quantity to consider would be like concurrence between any 2 atoms. So this is also a valid and useful measure of entanglement between any 2 spins. And so we find that, so this plot is as a function of G on the x-axis, but with all the energy levels on the y-axis. So there is a maximum energy level because we are working with finites n maxes. So, but of course, in principle, there is no such thing as an upper limit. It will just go away to as high a value as you wish if you make n max very large. But for a finite n max, so we definitely see that the central band, the behavior of the eigenvectors inside the central band, so this is von Neumann entanglement entropy, is much higher in this region compared to the top and the bottom bands. Similarly, you can look at A dagger A, so which is basically the mean photon number, right? So this also is distinct from the top band and the bottom band, and similarly concurrence and also participation ratios. So these are all consistent with like the data that I showed with the energy levels. And So yeah, so this is like a quick summary of this part of the talk is that, you have the decay model, which has these three different kinds of phase transitions, and it's useful to think of the localization properties corresponding to the ground state transition. The thermal phase transition is well captured with the aid of mutual information, and in ESQPT also it is worth looking at these three separate bands separately, and also looking at eigenvector properties. So that's part one of my talk. So part two is about...
A question.
Yes.
The properties that come out of eigenvectors, the quantities,
Yeah.
As opposed to the eigenvalue quantities, the sensitivity to cutoff is it more or less the same, or
it's more or less the same? Yes.
So the eigenvector properties are not more sensitive, or?
No. So they are. So we have checked that these properties are robust as a function of nmax. So I'm not showing you data here, but we have done the study. So here, for example, we have taken nmax to be relatively high, and then we fix small n, capital N, and change this, and then we have played these kinds of games as well. But sensitivity is more or less the same, whether you're looking at eigenvalue properties or eigenvector properties. And the main message, of course, is that there is this central band. No, even if you take nmax to be very large, your this level will keep on going up, but this upper band will always remain for all the nmax that we're able to reach. Right. So in that sense, yes.
Element, is that right?
Yes, that is true. Yes.
Okay, even though it's localized, but
so this is like entanglement between all the spins with respect to the bosonic field. But if you look at individual spins, they are not entangled. Yeah, so I have not shown you data for that. We also have data for, you can ask how entangled is one spin with respect to something else, or study something like the purity. So if you're in the normal phase, so they're basically they have their own individuality. But and also, you should also be careful about if you're looking at the small patch there is, which is the ground state alone will have some slightly different properties. But as you go higher, the entanglement is quickly it's much higher. Okay, so we'll come back to this again when I go to part two as well. So part two is about the same kind of a model, but where I introduce some anisotropy in the decay model, right? So this is about this paper where Dibyendu is also a co-author. And so we got interested in this after we saw this paper by Vladimir Gritsev and co-workers. So where they showed that, in fact, if you put in some anisotropy, in addition to these three kinds of phase transitions, the QPT, ESQPT, and the thermal phase transition, there is also an ENET. So in fact, their entire focus was on the ergodic, non-ergodic transition, as they called it. So I will describe the model. So there is a G1 and G2. Now there are two parameters. So the decay model itself lies along the diagonal, right? And so we looked at this, and then we thought, okay, what will happen to entanglement properties? What will happen to eigenvector properties, and so on, which we investigated in this work. I will show you what our own findings are. So the main message from this part is that again, there are it's a rich set of phase transitions. Now there's also an ENET which comes in, and once again, it is useful to look at von Neumann entanglement entropy, participation ratio, multifractal dimension. Again, there is a change to, so multifractal behavior also features not only at the ground state level, but you'll see that even excited states are also profitably studied with the help of the multifractal dimension. So I will go over the details, and then we'll again look at this the main message will come back again. Okay, so the model now is exactly like before, except now we have separated this rotating term and the counter rotating term, and we have put these two different couplings. So there's a G1 here and a G2 here. If you put G1 equal to G2, then you get back the isotropic one, which we already studied. So this is in some sense a generalization of the decay Hamiltonian. And so there is so when you're working with, so there are two main transitions which I want to focus on for the purpose of this talk. There is also an ESQPT, but maybe which I will not discuss here. And these two transitions are actually well captured with the aid of these two pictures. On the left-hand side, this is the ground state quantum phase transition, which is very similar to the normal to superradiant phase transition, which I showed you already. And so that lies along this line, right? So here I have a plot of inverse participation ratio. And so in fact, what was GC was equal to 0.5 in the isotropic decay model. Now that becomes, is now a whole line of phase transitions, which is given by G1 plus G2 equal to 1, right? Which separates the normal phase in this darker region is the normal phase, and this lighter region is the entire region is the superradiant phase. So this is at the ground state level. And so if you look at all the eigenvalues, so this is, I mean, like you can say it's a reproduction of Gritsev's paper's results, except that we have some fine-tuned way of looking at these eigenvalues, right? So in our, so like I said in the previous part of the talk, it's helpful to think of a central band, separately analyze only the central band when you're looking at the eigenvalues in the superradiant phase. So this entire region, so we have actually looked at eigenvalues drawn from the central band, and then if you compute the R ratio, this region corresponds to Wigner-Dyson, and so this darker region is all, they all correspond to Poisson. So this is like non-ergodic phase, and which comes from looking at the level statistics corresponding to, you know, the entire spectrum, right? So these are the two kinds of main transitions which I want to focus on here. And so this is all is our own data, which shows that, you know, first of all, the ground state phase transition is, you know, well captured by a bunch of different quantities. One is, I mean, you can just simply look at the ground state energy. So the ground state energy in the entire normal phase is pretty much the same, and then it dips the moment you enter the superradiant phase, and it's very stark, this this transition. So you can see it very well just looking at the energy itself. But also, if you look at the average boson number, so this is where the term superradiant comes from. So it is like, I mean, the superradiant phase contains, you know, lots of photons, right? I mean, it was originally like a quantum optics kind of model where people saw that this region has, you know, enhanced number of bosons which are present, whereas in the normal phase you have very tiny number of, you know, the number of bosons is very small. And so this plot is about the localization properties. So if you look at IPR in this region, so this entire region, you see that IPR is close to 1, whereas here it is very tiny. So it is localized here, and I mean, this region is definitely not localized, but I will, yeah, so this data in fact shows that it is multifractal in this entire region. So what we showed for the decay model was along this line, but in fact in this work we show that it is true for any generic point. So like here, for example, I have taken G1 and G2 to be 1.2 and 0.8, some generic point in this region, and then if I study the PRs, the scaling of this PR, it also goes as roughly like square root of ND, and so there is also this confirmation that this is true for very large values of the cutoff Nmax. In the inset we show that it is all, it's robust against increasing Nmax, and so this multifractality holds, right? So generically in the superradiant phase. So this is one point, but so interesting observation we made during this study is, if you looked at the participation ratio, not only of the ground state, but various excited states. So if you look at the this region, this is basically a repeat of the previous one, but I have plotted participation ratio instead of IPR. Participation ratio, so this is for the ground state, so which shows you the normal to superradiant phase, and then you go to some 10th excited state, then some 100th excited state, and so on, and eventually when you come to the middle excited state, so then you see that this picture is closely resembles the level statistics picture. So in fact, the participation ratio itself is it shows that in fact, so as you go to very, you know, you go to high excited states, middle excited state precisely, you encounter, so this region is, I mean, it's, one can also look at the multifractal dimension. So you see multifractal dimension in this region is, for example, is a green color is somewhere here close to 0 localized behavior, and here it is close to 1. It's well, I mean, it is actually close to 0.5, which we showed. And then in the other regime, this is the entire region is the ergodic phase. You see that D1 is close to unity here. So here you have a scaling of participation ratio, it goes as linearly, whereas this region becomes now the scaling turns around, right? So it is, it's helpful to think of participation ratio not only for the ground state, but also for excited states. And you're able to recover the same kind of contrast using eigen vector properties as well. So this is yeah, one message. And then, okay, so we don't have much time, so I have to rush now. Okay, so TC. So if I look at TC again, mutual information is an excellent way to capture this transition temperature. So, and I'm going to just quickly sort of slide through this, and we'll go to the main thing which I want to talk about, which is about the effect of periodic and quasi-periodic drive. So this work was published recently, and so Leah Santos is a co-author on this. And so here what we do is we introduce a periodic drive, and so the high frequency Magnus expansion, we are able to actually write down an effective Hamiltonian which works very well in the high frequency limit. And then, so if you use a periodic drive, the system saturates to a steady value, but it is not going to heat up to the infinite temperature state. On the other hand, if you use a quasi-periodic drive, so there is a long pre-thermalization window before it heats up to the full ergodicity, regardless of where you start from. So this is the main message from this part. So this is the driven decay model. It's exactly like the anisotropic decay model, except there's going to be a time dependence here, G1 tilde of t and G2 tilde of t. And this I'm going to take, this is going to be the driving protocol. There is some amplitude omega, and then your Hamiltonian is going to oscillate between h plus v and h minus v. So this is the undriven model, and then v is given like here. So this is the protocol we are considering. First, we will do it with periodic driving, but also I'll show you data for what happens if you have a quasi-periodic driving. So the high frequency expansion, so you start by writing down this Floquet operator. You want to get to this HF. I mean, the exact expression is not possible, but there is a way to do this Magnus expansion, and since it's a time-independent parts are involved, in fact, this reduces to simply a BCH kind of expansion, which you can do and write down H effective, and in terms of these x's and y's. So this is simply writing, expanding out this in terms of BCH formula, and we go to order in t squared. So when we keep order to t squared and carefully do this algebra, there's a lot of very complicated stuff which you have to just simplify and spend a lot of time if you do it, and then you end up with an expression like here. And so here you see that, I mean, of course, if you put t equal to 0, you get back this. So this is the high frequency limit. It's going to be exact, and it becomes like an undriven system itself. And so what we see is that if you study the this ground state properties, so you can show that in fact this G1 plus G2, which was equal to square root of omega omega naught, defined for us the quantum critical line for the undriven model. Now there's a correction to this, and then you have a line which goes something like this. And so this way we did it analytically, but we are also able to show it with the aid of this IPR, and for small t's indeed this works out quite well. So using the effective Hamiltonian picture. And so then we looked at the level statistics of the effective Hamiltonian. So, so if you look at the top panel, so this corresponds to G1 equal to 1.25 and 0.1. So in the high frequency, so on the x-axis we have omega. So if you are at a very high frequency, then it is going to the Poisson value. So that means that, I mean, the values that you have chosen for G1 and G2 are in the integrable regime. And on the other hand, if you choose your G1 and G2 to be in the ergodic regime, and if you look at the large omega d's, it's going to go to the ergodic point, whereas at very tiny frequencies, it has been argued also in other studies, and we also see that in fact R value goes to the value corresponding to the circular orthogonal ensemble. And so what is interesting is that there is this dip that you see. So right in between, it appears that there may be some special frequency that you can tune such that in fact you can generate, you can start from a regime which is ergodic and then create non-ergodicity in a, you can, with the help of a drive. So by the way, it's also important to observe that, there is data I have shown you for from H effective itself, that is somewhere here. It agrees very well for higher frequencies, but eventually it fails. I mean, for low frequencies, it is not supposed to agree. No matter how many orders you keep it, it's going to fail. But for high frequencies, you can see that it actually does a very good job. Right, so yeah, so it turns out that this dip down to the Poisson value is a bit of an artifact. And so in fact, Yeah. Okay, so the figures on this side are simply the same data, but with omega d scaled by the bandwidth. This is just to show that this is like robust against Nmax and everything. It's legit, whatever data we have and so on. But essentially, the main message here is that for high frequencies, H effective works out very well. But energy statistics seem to suggest that there is a way to tune your omega d to get non-ergodic behavior. But then we will show you quantum dynamics. So if you do directly dynamics and study quantities like the average boson number and the von Neumann entanglement entropy, so there is this page value which one can identify because we have truncated this Nmax. So there is a S page which one can compute, and so we show that in fact if you start in an energy a low energy initial state, right? I mean, so just focus your attention for the moment on this part of the slide. So you have so this is the bosons, the time evolution of the number of bosons as a function of time, and then you have the entanglement entropy between all the spins and the bosonic mode as a function of time. So you see that when omega d is small, so this actually tends to go to the page value, and when omega d is very large, the entanglement entropy goes to the same value that is given by the H effective curve. And so there is nothing to suggest there is some non-monotonic behavior in between, like what was being suggested by level statistics. And so indeed, so we believe, like has also been stated in like earlier works on similar systems. I think there's a paper by Marcos Rigol and co-workers where they argue that this kind of a dip is an artifact of this folding which happens when you're considering frequencies and which you have to be reconstructed into your Floquet-Brillouin zone, right? So there's R average showing a dip down might be an artifact, and since we also don't see any signatures of it in the eigenvector properties, we also think that is the case. And so I have only a couple of minutes, so I'll quickly show you data for the quasi-periodic drive. So there are two different ways in which we consider two different protocols within the quasi-periodic drive. One of them is using Tomaz sequences, and the other one is using Fibonacci sequences. So we find that eventually it doesn't matter where you start, doesn't matter what your G1 and G2 are, the system will always harmonize. It will go to the page value. So entanglement entropy goes to the page value, and a bosonic number also goes to the value corresponding to the infinite temperature state, which you can compute what it is, and it exactly agrees with this. And so the only thing that these parameters and the frequency and all can do is change the amount of time spent in this so-called pre-thermal phase. And if you start at a higher value of the energy, so you can also look at what happens if you start with lower energy or higher energy initial state. If you start with a higher energy initial state, you find that the pre-thermal value of entanglement entropy itself is higher, and then you stay there for longer before thermalizing. And you can also study how this heating time, how does it go with the frequency, but also how it goes with the initial energy and so on. And if you do it with Fibonacci sequences, you also find that heating time is even longer here, right? Because Fibonacci sequence, so like it's shown in this picture. So Tomaz has a bigger spread in its Fourier spectrum, whereas Fibonacci is fewer frequencies are represented. Therefore, it takes longer to go to the page value if you're working with Fibonacci. So I also have a joint a plot with all the different plots of periodic drive just stays here forever. It doesn't go to the page value here, whereas Fibonacci and Tomaz will eventually get there, but there may be very long pre-thermal times involved, right? So this is the main message. I have not actually done justice to some of the details, but they're in the paper, which I invite you to check out. But I want to quickly advertise this paper, which was published yesterday, so it needs to be advertised. So, I mean, this work is about, so here Sebastian Moessner is also a co-author. So we propose and investigate a disordered single mode decay model here. So, and then we show that the quantum phase transition now can show up even if the mean of your coupling is 0, but if your standard deviation is sufficiently large, even that can get you into the superradiant phase. And in fact, we have an approximate curve which works out remarkably well for the quantum critical line. And there's also a way to analytically derive the critical temperature and numerically verified. Once again, mutual information turns out to be a wonderful quantity. So this is the model we have, where you have so we have all these GIs here, which are drawn from a distribution with some mean and width. And so you see that this data where you have energy and you have ADAG array. So this is the analytical expression which comes from this simple-minded analysis. It turns out to be quite a good description of what actually happens. And also we are able to work out a very nice expression for the transition temperature, which once again seems to work very well with mutual information. Okay, I think that's all I want to say. Thank you.
Thank you. Questions?
Yeah.
Yes. Just wait a minute. So about the part where you see a dip in the gap ratios, but not in eigenstate measures.
Yes.
So one thing that can happen in gap ratios is when you have a small number of independent random matrices, the decay is very close to the Poisson value, but the eigenvectors will still be like delocalized over most of the bases. So do you think something like that might be going on?
Yeah, so one argument which is also well enunciated in this paper by Rahul Nandkishore and a co-worker, I don't remember his name, is that if you have a bunch of eigenvalues which have to be folded into your minus omega d by 2 to plus omega d by 2, if you're with respect to your delta. So you have to consider these three different cases. Omega d is much lower than the bandwidth, omega d is much greater than the bandwidth when you don't have to do any folding at all, and these intermediate values. So it is in these intermediate values where we are seeing this kind of a discrepancy. And so one sort of hand-waving argument we have in mind is that, so maybe in this intermediate region, somehow the higher, most excited energy levels are the ones which are most affected by this kind of reconstruction which is happening. And the lower levels are more like Poisson, like you saw in the first part of the talk, where we were showing these three different bands. So the lower levels, so this Poisson behavior tends to dominate. And that is why, so I mean, the fact that it's going all the way down to Poisson, I mean, the other studies which have seen a similar behavior, there's a dip, but the dip doesn't take it all the way down to 0.39. So that's why, you know, people were quick to dismiss it as some kind of an artifact. But in our case, we spent a lot of time thinking maybe this is a genuine thing. It's actually going to Poisson. But the dynamics, there is no signature at all in the dynamics. So now we tend to believe that this is also an artifact.
So then just a quick comment.
Yeah.
So something like the gap ratio, that's not very sensitive to when you have like several large random matrix blocks. So it approaches Poisson very quickly. But something like the spectral form factor might still show a ramp that's very sensitive to that and distinguish between that and Poisson. So you might want to like try something like that.
I see. Okay. Yeah, we should think about it.
Okay. So, I mean, is this a true phase transition at all, like finite temperatures, or
In the last part?
or in the just the normal decay model?
A normal decay model, it is
Finite temperature.
It is a finite temperature transition.
Yes.
Sorry, I just missed the conclusion of the last part. So is the point that the disorder shifts the critical point, or what?
Yeah,
what is
so actually there are two interesting things here. One is that you see, if I put sigma equal to 0, that means there is no spread at all. That is like the usual decay model. So you go from the normal to the superradiant phase. So what is interesting is, even if you have mu equal to 0, you can simply play with a standard deviation. You put a spread around a mean value, and you can still get a change from normal to superradiant phase. So that is one aspect. And the other is that it looks like it's just like an RMS value. So you just basically equate the RMS value to the critical value, and this seems to work out quite nicely. And that is also shown in terms of the transition temperature. You see here, we are putting in an average of G squared, and there's a whole line of arguments we have included in the paper, which bring us to this expression. A little bit of some approximation is involved, but then the final sort of test is with mutual information, which we have established seems to work very well. And that also again confirms that this expression is it's nicely borne out, right? You can have mu and sigma. You can play with both mu and sigma. That is the interesting aspect of this model.
Okay, thanks.
Yes.
Yes.
So in this anisotropy decay model, you have considered the same driving frequency for both counter rotating term and rotating term, right?
Yes.
So what will happen if I consider some difference between this thing?
Yeah, so that would make things.
So
I
can
don't
there
know.
be
So
like
then it will make it somewhat like a quasi-periodic driving.
quasi-periodic, effective quasi-periodic? So,
Perhaps, yeah. There's
so
not
the effect that you are observing for quasi-periodic, can that also be observed for that?
Perhaps my guess would be that it will tend to thermalize it. Yeah, because you're bringing in two frequencies. Yeah, so probably, yeah, we will have very long lived pre-thermal states, but it will probably eventually thermalize, I would guess.
Okay, we have to move on. Thank you again.
Okay, thank you.